All right, mic's working, great. Thank you guys for being here this afternoon. I know it's last talk of the day before the lightning talks. Hopefully this is really cool and exciting. If it's not, that's on you, because this is really exciting to me. I'm going to talk about deploying machine learning using Sklearn pipelines. My name is Kevin Goetsch. I'm at Grubhub. I was at Braintree and Allstate before that. I'm really into using Python in my machine learning. What is this talk about? Pipeline is an overused term. Every freaking library uses this term. I'm going to talk about a very specific pipeline. It's a technique inside of a library, Sklearn, inside of a language, Python, that I'm using to do machine learning. If I say pipeline, I'm referring to this one thing, not all the other uses of pipeline throughout the entire programming community. All right, we're all good with that. Why are you watching this? I'm going to guess that maybe you want to understand how to build pipelines and when to use them. Yeah, all right. Maybe you want to learn how to do smooth development and deployment. This one's really, a lot of very good data scientists not know how to use pipelines. And it's really simple, and it's really helpful, and I would love to have you guys use it because it makes it way easier to deploy your work. You might also be my father trying to understand what I do at work every day. I am so sorry, Dad, this is not going to really help. We're just going to keep working on that. Here's the roadmap for the talk. We're going to talk about what pipelines are. I'm going to give you a modeling example. We're going to do kind of a piece-by-piece walkthrough of what goes inside of a pipeline. Then we're going to kind of check in, make sure we're good. Then we're going to talk about the life cycle of data science, mainly development followed by deployment. We're just going to wrap it up. Yeah, easy peasy. It's kind of a chicken and the egg problem. You kind of have to understand the life cycle to understand how it fits together. So I'm just going to plunge in where I'm going to plunge in. We're all going to go with it. And by the end, I hope it all comes together. If it doesn't, I love questions, as all my coworkers who are here know. What are Sklearn pipelines? A container of steps. What are steps? The main ones here, estimate. Did my mic cut out? Nope, we're good. Pipelines are used to package a workflow and package fit model objects all together into a single serializable object. I'm sure they're used for lots of other things. This is the talk. Did I miss a slide? No, cool. All right, so I'm going to do a quick visual because this is actually how I think of it when I start building pipelines. They're like Legos. You're just stacking little component pieces together. One of the big advantages of using pipelines and all of their component steps is that it is super modular. You can actually just take out and put in different pieces. This is literally, I visualize it like this. So we have an estimator. It's going to be this salmon-covered box. It's just an estimator. It's sitting there. It maybe takes an input, maybe has an output. Let's not worry too much about it. It's a little Lego block right now. All right? There's also maybe a transformer. The transformer does some sort of transformation. They're kind of sitting on top of each other, but they're not actually squished together yet. There's no communication between these two right now. The pipeline is what snaps them together, right? And pipelines snap things together tall-wise. We're just talking about stacking Lego blocks right here. It doesn't really matter to the pipeline what's inside of it as long as it can just transform and pass the output of one to the input of the next, on down the line. Here are two towers, two pipelines, right? But these are just stacked side by side. They're not actually communicating across. Hopefully we all see this was going because there's a fourth part, and that just fits the two together, right? So feature union just really joins the result of whatever steps are inside of it. In this case, inside of this feature union, there are two pipelines, so the output of each of those pipelines are getting joined together. Inside of each of those pipelines, there's an estimator and a transformer. We're just this visual right here, fixed in memory. Good, because I'm going to actually look at some code next. And it's going to be simpler than this. But this is conceptually what we're doing. We're just stacking Lego blocks. We're just joining their output. So I wish I had an example as cool as that Eve one in the room next door last talk. That was really cool. I'm going to use the Titanic data set, kind of a classic, trying to predict who would survive the sinking of the Titanic based on data. We're even going to use a single predictor variable. We're going to keep it super simple to illustrate my points. Does this make sense? I'm the one with the mic, so I actually don't know. All right, so we're going to do this in a non-pipeline, like classical, just Python. I'm not going to lie. I just copied this code off the internet. It was from Kaggle. Thank you, whoever wrote it. I had a thing written about them earlier, but it disappeared. So response variable, you guys can look it up. It's like the first hit. Response variable, whether or not you survived. I'm going to load in some training data. I'm going to find the median age of the all ages that weren't null, grab the median age, and then this nice little if length of training, blah, 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 that's just going to replace all null values of the age with that median age, right? So we don't have any nulls, we've just assigned the median, we've made this choice, feature engineering maybe. Keeps flashing, I'm not sure if it's up there. And then we're gonna drop all the columns that aren't relevant to our model, right? So we're just predicting survived, we're just using this one variable age, which has been adjusted. Neat. Now I'm gonna load some test data. I'm gonna do the exact same thing, find the median age, do the replacement, drop the other variables. I'm gonna start a random forest classifier. I'm gonna give it a random state so that we can actually do this in the pipeline world and get exactly the same answers to prove my point. It'll be awesome. I'm gonna fit. I'm going to call predict prob A on my test data. I fit on my train data. This should all sound familiar to most people after all of these talks. People have really explained it much better than I have, I hope. Because, yeah, I'm a little embarrassed, but it's fine. So I'm gonna redo all of that work with the pipeline. To recall, the output of this thing is called forest output. I'm really into very explicit variable names. All right, so here's redoing it with a pipeline. We have a response variable. We're gonna read in both training and test. Then I'm gonna call this function make pipeline. As you can tell from how many times I've said pipeline so far, I'm going to go more into this later. We're just gonna kind of take this as a thing for now. But this is the Lego blocks again, right? You can see, visually, there's 4 steps, right? I have something called a factor extractor, which does age. I have a fill in A, which I hand this training median age. I convert it back to a data frame. At least that's what I hope the function that says convert to data frame does. Then I hand it a random forest classifier, right? So in essence, I formed a pipeline around these 4 blocks, one stacked on top of each other. That's all I did. I haven't actually done anything with it until I call pipeline.fit. Now it's a fit pipeline object. And then pipeline output, or pipe output, is pipeline.predictProbA on df test data. You'll recall that earlier, when I was doing the normal training, I had to like say which variables to hand off, this sort of thing. The pipeline is doing that by having a factor extractor. All right, so they should match, right? And they don't. And then I was writing this presentation last night, because they gave me like 3 days to write it, which meant I played video games for like 2 days, and then I wrote it yesterday. So this kind of freaked me out last night. I was like, did I not understand what I was giving a talk on? But then it turned out to illustrate my point. Earlier, when we were doing this manually, we said median age is equal to the test data frame age, drop NA, so don't count the nulls, that median. Took me a little while, but I realized that the test data frame median age is not the same as the training data frame median age, right? 27 and 28. This is just like a random sample of test and train. Easy mistake to make. I definitely made it. I definitely missed it. But it serves to illustrate my point really well. You don't make this mistake in the pipeline, right? I didn't manually reapply my training. When I instituted this pipeline, I gave it 1 median age, right? I just said give it the training median age. And then it was fixed. When I called it on the test set, it just used that same median age. The same transformations were applied in both cases. This is one of those things that, could you do this without a pipeline? That's a common theme in my talk. You could do all of this without Sklearn pipelines. There's nothing like unique about this. It just saves you hassle. Reality is really hard and complicated, and I'm really lazy. So if you can save hassle and be right more often, oh my God, so nice. So we ran it all, right? Fixed that median age bug, and the pipeline and forest output are true. It's super common. Yeah, I guess this exact mistake is common. Didn't take me more than 5 minutes to find in the code, but if there were maybe 20 variables with some more complicated interactions, and maybe they were spread across like 2 days worth of work, and maybe a coworker did part of it, like this is where it starts getting complicated. Can you institute really good programming practices to avoid this? Of course you can. Do you trust your coworkers to do that? No, you probably shouldn't. I don't really trust past Kevin to do that, and you know, it's me. So, modeling. This is the code wrap-up part. I only had to write out my transformers, my whole sklearn pipeline. I wrote it once, right? It was one place, easy to find, easy for me to read. It's also easy to swap out pieces. If I decided median age wasn't what I wanted, maybe just mean age is what I wanted. Bam, I just swap it out in the pipeline definition. If I wanted to do it in the classical example, I'm now doing it in 2 places. And 2 places sound like way more work than doing it in 1 place. And you can multiply this out by all your different types of things. But in the end, it's just simplifying your work, simplifying your workflow. Readability, yeah, I do curse past Kevin many times. Converting all my work to pipelines has reduced the amount of cursing past Kevin. It's really nice when you go back to your work 3 months later and you actually know what the heck happened. Maybe this is only my problem, in which case you guys are lucky. Finally, keeps all the intermediate steps together. This is the mistake we made, right? Like, you want to keep these steps in one place. You don't want to reapply all the steps. You want to just build once and just apply it consistently across all your training data. Cool. Right, so I promised it was kind of a chicken and the egg, so now we're going to go a little deeper. I just kind of gave you a make pipeline and expected you to trust me on it. We're going to look at it a little bit deeper, though frankly Tom's talk this morning was like more complicated in the transformer realm, so talk to him if you have questions. He apparently knows this much better than I do. What is a transformer? Right, transformer is one of our little blocks. I believe it was green in my earlier visualization. It's got several methods. It's got two main ones I want to worry about. It's got transform, which applies transformations to the data. And it's got fit. It applies fit logic on X. Most transformers don't really use fit, except for the example from Tom that was awesome, so this is just Tom. When you call fit, you're not doing anything in this simple factor extractor, and this is the same factor extractor I used earlier. You give it a factor when you initialize it. I gave it age as a string. When you call transform, it's just going to return to you the slice of data where age is the column, right? There's nothing fancy about this. You can do it manually. They're the same thing. We're just sub-slicing the data. Why would we ever do this? Because the world gets really complicated really fast. In this way, if I have a whole huge stack of Lego blocks of transformations and fancy things going on, at the very top, I know what's going into it. I can just say, I know age is going into this. If suddenly, like, I'm doing this happens when you don't do a proper drop column, or maybe you're rewriting drop these particular columns and you miss one, you misspell it, you miscapitalize it, suddenly you're feeding extra data in, you're trying to debug your own code. It just clarifies it. It's a little more verbose. I use this a lot, especially with my coworkers who I force to kind of use this in their deployments. When do you start like doing all your hacking, and then when do you switch over? Yeah, Young, I can see you smiling. When do you switch over to actually using pipelines in development? And I use this all throughout development. It's much easier for me to just put it in this context to begin with. Estimator, that was the salmon covered box. Not really gonna go into it. It's just a general term for any sklearn object that makes a prediction. Mainly it's got a fit method and a predict method. If you were paying attention earlier, I actually called predict prob A. There are definitely other methods. For the purpose of this talk, we're just kind of focused on like you're fitting a model object, and then later you're calling a predict on that model object. That model object is something like a random forest classifier. Here's one instantiated. It's got a bunch of metadata with it. That's not really important. It's actually just an estimator as far as the pipeline's concerned, because let's talk about what a pipeline is. Am I going too fast? I've been known to. But I have way more slides this time than ever before, so I'm going to keep going. Pipeline is a whole stack of transformers with an estimator at the bottom. Is this universally true? Of course not. I will show you an example later where it's very different, and we get into ensemblage and hierarchy models. But the classic example is a bunch of transformers with an estimator at the bottom, which is why pipelines, when you call transform, they call fit then transform on each step. When you call predict, they just call transform on each step. This is really important. Transform, 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 and predict on the final step. So earlier you saw my factor extractor. It didn't have a predict method. I'm calling predict on the pipeline. The first object is this factor extractor. The pipeline's not calling predict on it. Pipeline's just calling transform, right? Because they're just Lego blocks. Easy peasy. It's really useful. Make pipeline, that thing I called. Oh, right, so initialize, you pass a list of tuples with the name of the transformer or estimator followed by the actual object. This gets really verbose really fast. If you do this a lot, they have a shortcut. It's called make pipeline. It just skips that. You hand it a bunch of objects, and it creates that list. I think I even, did a little code example. So make pipeline, our earlier factor extractor, fill NA. These are all transformers, convert to data frame, transformer. Hopefully you know what convert to data frame looks like mentally, like it's a transformer. In the transform method, it's like pd.dataframe. We're just returning that of the data that you handed on down the line. And then a random forest classifier. That's identical to this, right? Factor extractor, actual object. Bam, 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 bam. This, I'm just lazy. It's a theme of my life, definitely of my talk. This is faster. That's why I use it. It's still super clear to read to me, make pipeline. Feature union. Final thing, feature union. Final of these 4 different steps that are contained within this paradigm. It's basically a horizontal pipeline, right? If pipelines are stacked up tall, feature unions are just wide. So Feature unions have a bunch of steps, but now they're in parallel, and they're just feeding the output together. The main thing you're going to call is something like transform, which is going to call fit then transform. Eventually you're going to call predict. All of this kind of stuff happens. I'm kind of just glossing over it. The docs I find are super readable, but that could be an indication of what kind of person I am. I think it's really straightforward. It's just doing the same step that the pipeline was doing. If it doesn't look straightforward, I definitely didn't think it was straightforward 2 years ago. So it does take a little bit to get in, but this is used more and more, and so the more you see it, the more you can play with it. I'm going to get to it later, but you can actually pull out each individual brick of these towers and play with them. You have access to all of these objects. It's not like they're locked away from you. So merge is the final result. Same initialization, name and transformer. You can also call a make feature union. Caveat, I've written a data frame union class, so I sometimes flip up and call it one or the other. It's just the same as feature union. It just outputs a data frame instead of a NumPy array. I find it easier to work with Panda data frames. Is it as performant? I have no idea. I don't really care. I work with small enough data that it's just easier for me. It was super simple. I just read their code. I shouldn't say simple. It took me actually weeks. I was really happy when I did it. And their code was super good. That's what I should say. Once I got into it and read it, I was very happy. This is useful to me. I would be happy to share it. It should be useful to others if they want it. So let's talk feature union. Yeah, we got a feature union right here. Feature union equals make data frame union. This is making one of mine. We can keep it thinking as a feature union. They're virtually identical. But this is that same little visualization. 2 objects inside of the feature union. Pipeline 1, pipeline 2, right? We're calling make pipeline. Inside of pipeline 1, a transformer followed by another transformer. Factor extractor followed by fill NAs. Inside pipeline 2, we have a factor extractor followed by a fill NA followed by something I called categorical dummifier. This creates dummy variables for categoricals. I reuse this a lot. It's a pretty standard transformer. Unlike Tom's example with pandas, other people, someone else went to Tom's talk, right? There were only 2 rooms, okay. Unlike Git, or I don't use Git dummies. I didn't actually know that it had that like drop first, which looks like it was just released in 0.18. I use Patsy, which drops that first, so we don't. Doesn't really matter. It's going to transform to a categorical variable. So we have our training set, just the first 3 rows. All we're going to do is we're going to just call on our feature union object fit transform, right? And this is just 2 different pipelines. Each pipeline is doing its thing, producing an output, and the data frame union is joining them together. Yeah. So what we get is sex true dot male. That's how Patsy writes its categorical variables, and it drops the female variable because of because there's only 2. Age, well, doesn't actually look any different because I didn't have any NAs in my first 3, but it would have been replaced as well. And the age column was produced by the first pipeline in my feature union. Sex was produced by the second pipeline. Yeah, this stuff's really, really fun when it starts just kind of clicking together. I think Legos are fun too, though, so. Okay, check in. We're all good. You're now all experts, right? We're all experts. It's only going to get cooler from here. In what pipelines are. You know kind of how to build a basic pipeline. It's called make pipeline. You also know kind of what each piece of these are, I hope. Even if all you take away is that they're Lego blocks, that's probably pretty cool. Next up, we're going to talk about data science lifecycle, just generally, especially with development and deployment, and kind of where these pipelines are used. All right, so as I advertised, model development. I am probably not even going to talk about cross-validation. Some of the main steps in an ideal model development environment: feature engineering, model selection, hyperparameter optimization, cross-validation, publishing the model. You probably heard this 100 times if you've been to talks like this. If you've never heard this before, this is kind of the quintessential building a data science model. In reality, it's way more chaotic and just creative, in my experience, because all kinds of things are changing all the time. But yeah, again, it can be accomplished without pipelines. I don't want to, you can do it however you want. Pipelines are just a tool that I find are easier for me. Why I heart pipelines, part 1, emojis are hard in Markdown. At 11 p.m. last night, I could not get it to do an emoji. We're just going to live with it as is. Feature engineering. Reuse transformers. This is awesome. I love this. I use my categorical dumbifier in all kinds of projects, right? I have it in a shared data science library, and I just import it. I don't have to reinvent how to do this. If I want to strip the dollar sign out of like a dollars and cents column, I just have a like convert currency to float. I just call it all the time. It doesn't really matter where it was first used because it's a standard one. I have a separate separate like transformer list for very specific projects that have weird transformers that wouldn't be reused. But being able to reuse your transformers project to project is awesome. If you find a bug in one of them, you can fix it in all of your projects instantly. You just also have more standard code. You can think about this once. Again, God, I was just so impressed by Tom's talk. With the whole doing like a reverse transform, when you want, or inverse transform, when you want to pull data back the other way, you only have to write that once in that particular transformer, and now you've got it. You've got it on all of your projects that you're using this in. Right? Readable transformation logic. I find it super readable. You have a stack of these things. You don't have to find where in the code this happened. It's super readable. Readability is really important. Future you, coworkers, all of that. Apply identical transformations to training and tests. Remember that mistake I made earlier? This is just one of those mini gotchas in data science that you avoid entirely by using the exact same feature engineering pipeline. Like everything comes through. It's hard to mess up. I can still do it though. Don't trip, yeah. You can put anything in a wrapper. This is something that was, this is slightly complicated and I'm gonna walk through it line by line. So get ready or open your laptops, your choice. This is something that I implemented to do extreme gradient boosting as part of an ensemblage package in our modeling environment. So two things here. One, this extreme gradient booster, which is not the Sklearn paradigm, did not want to be the last thing. So line, this will be the final thing. This is going to be the second last thing. But I still needed it to produce a prediction. Two, it is not, means I can't count on it having fit trans. We just can wrap it. So we're going to call it a transformer mixin and a base estimator. This gets me some of this fanciness where if I call fit transform, it will call fit, then transform without me having to think about it. It also provides things like get params. Some of the stuff that makes the internal workings work nicer, I just import both of these or assign them to about half my classes by default. I'm not going to go into detail on those. The actual object, right? This is a transformer object containing an extreme gradient boosted model. Important distinction. Differentiation. It's got a name. It's got a model object, which is the actual extreme gradient boosted library's model object. And it's got an evaluation metric. When you're calling predict down through this pipeline, it doesn't natively pass an evaluation metric. I wanted to be super explicit, so I have it in here. I assign it ahead of time. Should have back up. Ensemblage. So, data frame union, multiple pipelines. When you combine the output, that's an ensemblage. You could just take the average of two pipelines' outputs, and that would be an ensemblage. You could use somewhat thinking way more advanced. It doesn't really matter. When I'm saying ensemblage, I just mean taking multiple pipelines, combining their output. Let's just say an average. Average is great. It's super easy to understand. So, back in here. The fit method. I'm going to take the model object. I'm going to call fit on it. When I fit it, I need to hand it this evaluation metric and some arguments. In this case, the x and y values. Now inside of this transformer, I now have a fit object. So when I call predict, I need to call predict on this object. But when I call predict, it's going to call transform, 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 and then predict at the very end. This is second to the end. So transform, 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 transform means that when I call predict, I need transform to actually call predict on the model, right? That's why right here, it has a transform function. It says, in a data frame, self.model.predict on x. It's also going to name the column this model plus underscore prediction. So we have 5 different pipelines. They all kind of look like this. This is all their last step that we're unioning up or taking the average of at the end. And each one's going to predict. Model 1 prediction, Model 2 prediction, Model 3 prediction. Then I'm just going to sum them up, take the average, what have you. Yeah? I'm really excited about this. This is cool. Because you can use anything. If you have if you want to get crazy, and it's really crazy, but if you want to go like R to pi, like you can use anything in here. You just wrap it. And suddenly you're calling it, right? It's super systematic, where it's just calling this transform. You know exactly what it's doing. There's nothing really complicated under the hood here. Yeah? All right. I get excited about a lot of strange things. Model selection. This is still part of development. These things are super modular. You can take out pieces, put in other pieces. If I didn't like my random forest and wanted a logistic, I can literally just replace the random forest with a logistic in that one Lego block, and the rest of the tower is fine. It's going to do all the same transformations, feed the same thing in. I'm just using a different algorithm. That's awesome. That makes it way easier for me to play with things and tune things. As I get to in a moment about grid search, it's fun. It's fast. It's lazy. Tracking the interactions in the hierarchy of assemblage models. So assemblage models, when you get into like some of these Kaggle competitions, you get like 300 models predicting the inputs for another 200 models to 10 models, and that's your answer. And that's crazy sauce. How would you keep track of that? I wouldn't. I'd keep track of this, obviously. It's the whole talk is about this. It's super important to be able to actually track where all these things are going and coming. Pipelines. This was called Why I Heart Pipelines, right, as the section title. Not tracking intermediate data allows for easy model stacking. So this could also be considered assemblage, but you could use like principal component analysis, select your principal components, and feed those into a random forest, right, automatically. You can slap them together so you don't accidentally like save it somewhere in your code and then later call the wrong one because it was v2. And this happens all the time. It's great. Hyperparameter optimization, model tuning. Pipeline support, in fact, are heavily integrated with grid search. Grid search. Grid search is awesome. Grid search is simple. Overusing the word simple. Grid search is awesome. Let's stick with that. Earlier, we pipeline. I'm going to look at the pipeline's named steps, which is a dictionary, and the keys. I hope we all remember factor extractor, fill in A, convert to data frame, random forest classifier. I know, we're looking at code, right? This is just brutal. What a grid search does is it's just going to say, hey, how many trees do you want? And I'm like, well, is it better with 100 trees or 250 trees? You just give it a list of parameters, and it's going to run on each of those, and it's going to tell you which one was most accurate. Awesome. How do I say, hey, I have this huge Lego tower, and I want you to adjust blocks here, here, and here? You use grid search like this. So in this parameters dictionary, right? Everyone can read it somewhat? No? That's fine. The slides aren't posted anywhere. I can send them out, though. The dictionary reads random forest classifier, double underscore, and estimators. So all this thing is doing is scanning through your parameter dictionary, saying, OK, I'm going to find names of actual objects inside here, and then I'm going to look for a double underscore, signifies that we're going a level deeper, and then just hand that parameter to that actual step. You could go as deep as you want with double underscores, right? Because all of these can nest and nest and nest. You can pass it all throughout here. And you could mess with your principal component analysis at the same time. I create a grid search object. I feed it an estimator. Normally it would be like a random forest. In this case, it's the whole pipeline, right? Age, filling, all of that. And then I feed it a parameter grid, which is just a simple dictionary. God, simple again. I should watch that. Grid search dot fit. It's going to fit itself on this training data. It's going to fit 3 times because the default cross-validation is 3. And then it has 3 different candidates, right? This earlier list of 100, 250, and 300. 3 times 3 is 9. My dad and I are going to be on the same page for this part. You get a fit grid search object. From there, you can pull out what the best estimator was, what each of the different scores were. You can do all kinds of stuff. Key point here is I just fed it the whole pipeline. I didn't have to feed it like an individual piece of the pipeline. Cool, publishing models. So we've done all this model development. I'm not running out of time totally, but we're kind of getting there. You want to publish this model. Maybe you have a deployment process to S3, GitHub, maybe it's a floppy disk. You can just save this fit model object to disk. And it's really just joblib.dump, right? Pipeline, name of the thing you want to dump. It's going to write a bunch of files, because this is a random forest. You're going to treat that first pickled file, pkl, that's your main object. When you load it later, oh, spoilers. When you load it later, you're going to point at that same file, right? But you can do anything with these at this point. This is an actual artifact. And the artifact is not just the model logic. It is all of that feature engineering logic and your fit model object. I'm going to go stress that point a bunch more, so let's move on. Let's talk about deployment. Otherwise known as the 3-ish slides you've already waited like 30 minutes to see. because this is the name of the talk. Handing it off, right? You've got an entire pipeline saved to disk. It could be anywhere. At Grubhub, we post them to like asset buckets in S3. This is not a secret. This is simple, easy, fun to access. Fun for all ages? I don't know. All your deployed model needs to do is be loaded from disk into memory and had predict or predict prob A, what have you, called on that object. I can't stress this enough. You don't have to retrain your model. All right? You want to score new data? You do not have to retrain your model. You've made like a Java jar. You've actually created a fit object. This is the most common mistake I see, and it's super common and it's super obvious because at some point you have a new department and you want to say, hey, I have a bunch of code. It creates a model that then you can feed data to and get a score from and predict fraud. And they're like, great, let's put it in production. So you're like, here's my Python code. And so they put it in production. Your Python code trains the whole model and then calls score or predict prob A, what have you. Super common. I wanted to really make sure that this point was made. So I put myself a second note to emphasize this point. You don't have to retrain it, right? This is like rebuilding a car from scratch before driving it every time you drive it. We could talk a lot about model retraining, like how often should you do it and such. If your model, let's say, is a daily prediction, and you're retraining it every day on the newest day of data, you're prone to overfitting. If you're trying to predict who is sick based on hospital records, and they're testing based on your model, suddenly your model is eating its own tail, right? Because they're only testing ones you've said. Maybe you should just publish your model once on that old data, and maybe just retrain a model in parallel and see how they differ, or if they're the same. This sort of thing isn't thought about a lot in my past, and now it's really important to me that you actually really make sure you just use that same model. Cool, loading from disk. I did spoil this already. Let's say we have some totally random model, joblib.load, this thing called rfitpipeline.pickle. We now have some totally random model. It's got some named steps. It's got some keys. Yeah? They kind of look familiar? It's like we published it minutes ago. This is really cool. This is extremely cool. You can see everything that is inside there. So some totally random model, dot steps, gives me access to the steps. And then it's just a list of them, right? So I take 1, which is the second step because we're 0 indexed. And I get fill NA, the name, and fill NA, the function, with NA replacement equals 28. I can't tell you how much time and effort this saves me. There is stuff that is deployed in production running. Someone comes to you and they're like, hey, what are we replacing those nulls with? If you go back to your training code, are you 100% sure that you're going to get that same value? Because you can rewind your data and also recreate it and know for sure what was even put to production, which is great. But are you sure you can if it's some other coworker and they got a new job or they're on vacation and there's like maybe 30 different features and they have file sets that read like final _2 not this one, right? Like, have we not seen this? I see this all the time. It's a pain. In an ideal world, you wouldn't need any of this. You wouldn't at all have to double check this. You'd have beautiful version control and Jenkins deployments galore, and it would be great. But in the real world, pulling the actual object back into your local database and being like, so what was this thing, is really powerful. It really makes you move fast. Oh, I think I hit everything. Yeah. Data scientists are not data engineers. Data engineers are not data scientists. You can bring around coffee and donuts, or you can give them like a standard object. Either way, you're going to make real good friends with some data engineers this way. They don't want to deal with all of your bullshit. They're specialists. I'm skipping some things. I'll come back. They're specialists, right? So everything that a data engineer doesn't know about data science, you equally don't know about data engineering, right? They have their own iceberg of things below the surface that are complicated and interesting that they want to work on. This handoff, you want to keep it low friction. You don't want a whole bespoke process built out every single time a new model is ready to be deployed, right? So if you have infrastructure as an engineer that takes an object, loads it from memory, oh, this is going to my process, I'm skipping all over, loads it from memory, grabs some new data, calls the predict method of the object on the new data and outputs it, they don't really want to worry about, like, were you predicting fraud or were you predicting customer click-through? If it's just a pipeline, you get that. This is just standardizing infrastructure. This makes it really easy. But my stuff doesn't exist in a pipeline, you might say. You can write a wrapper for it, I might say, right? This is really easy and it makes your engineers happy. Are there going to be bespoke processes? Of course, everything is going to have some exceptions. But if 90% of your stuff goes this way, we're talking deployments that take minutes, not like months or days. This is really straightforward. I hope. I'm just going to keep repeating it until you believe me. That's really the approach I have at this point. Oh, right. I've had this happen to me. If your data engineer is on vacation, it's really nice if you want to like have something in prod and you don't have to like spend 2 weeks training the new data engineer. If they're just like, oh yeah, I see where they're just standard object, bada bing, bada boom, you're there. You got it. Just trust me, it was awesome. Why I heart pipelines, part 2. This is the development, right, was part 1. This is the deployment side. Tests can be written against pipelines. You can have standard inputs. You can get the output, save the output, compare the output from then on in every model version, see if they change. This is important. Models are backed up in version control. Again, modeling code should be backed up in version control. Having the literal object in version control is just an extra defense against any sort of failures. Rerunning the model that you did last December in a certain version is amazing. I'm hoping you can also rewind your data to that point. That's also really, to rescore it is often really important. This different times in my career has been more or less like the vendor break. Peers can check out your model and test it. Having peers being able to actually interact with your own model objects is really important. It means you can actually get some feedback, and just like to an engineer, it's a standard object, to an engineer, or to a scientist, it's also a standard object. They know how to load it, they know how to start piecing it apart, instead of like a huge amount of Python code that you're trying to read through and figure out what they actually did. This gives you that end result as an object. Cool. Open source is really cool. This applies to all kinds of open source things. You can write your own extensions, like I did with this data frame union, right? I can see the source code, I can read it, I can adapt it, and now I've got my own little thing. You can hire people who are already familiar with pipelines. This is not unique to pipelines, obviously. This is the whole open source community, and this is a big win in the open source community. You can actually hire people who are familiar. Everyone has homegrown systems. They exist. They're natural. Using less and less, it's really, really fast to get people onboarded. And you can collaborate across teams, departments, even companies, right? I get in arguments with random folks at different companies about these exact same things, and there's a whole community out there. There's Stack Overflow pages solving these problems. There are not Stack Overflow pages solving my homegrown company's tools problems as much as I wish there were. This kind of community out there, this kind of supports being able to work with different people is really awesome. Cool. So what I hope you walk away with. Kind of what an sklearn pipeline looks like. Yeah, stacks, Legos. Maybe where you'd use sklearn pipelines. Pro tip everywhere. You probably know that I think pipelines are really awesome at this point. And we all would probably agree that my father still has no idea what I do day to day. Cool, that's all my talk. The question is, when debugging, if there's something thrown like at the top of this tower when I called the whole thing, is there some way to really get at that naturally? It does give you the traceback of the actual like container which through it. And if you're having a lot of trouble, all I'll do is I'll just snip off the top 3 blocks or however many and call transform on those 3, because that will actually transform right above the bad one to be like, oh, the input is full of nulls. It's not the transformer's fault, it's right above it. Being able to just take is definitely how I debug these things. The question is, why did I roll my own class for XGBoost classifier? Because he thinks that the classifier has an sklearn class that implements these things as well. 2 answers. 1, I needed to have it for the ensemblage, so I had to have some sort of model transformer to call transform and translate that to predict to the model object. 2, I didn't Google enough. I had no idea that existed. The question is, why use pipelines or where to use them? So the difference between kind of pipelines and tasks and wrapping it there versus the Sklearn one, I have built both. I've had Luigi tasks, which are like a DAG, right? Like a directed acyclic graph. These different tasks are just calling each other. The code from Sklearn was literally just an object that is pulled in and called on. So the task is more of a like system level operation. These Sklearn pipelines are more of just the object. So when you're using these tasks, you might say like task A, transform the data by setting age null equal to this. Task B, do this. Task C, do this. Instead, you could just say task A, call my pipeline. Kind of. You can do both. It's really just a clarity issue at that point, and I can talk more in detail later if you want. They serve different roles, I guess is really where I'd say. Anything else? Back? Yes. Oh, sorry. Suggested that you can use grid search on top of a pipeline. The question was, can you also use that inside of a feature union? And the answer is yes. I have. The question is, does that become expensive computationally if you have a bunch of different inside of your feature union and these have different parameters? Yes, because you are running it, 27, 400 times. And you can tweak some of that around as needed. You can run those different model tunings. Like if you have a bunch of different parameters, you can separately. You can spin up some big server and just call parallelize and we'll have at it.
I guess what I was wondering is specifically will it call it 3 to the 10 times accounting for each of the various possible combinations?
The question is, will it call it, and basically a Cartesian join of all the possible combinations? For randomized CV, yes. There are other forms of grid search that do different things. But yeah, that Cartesian join, it really is searching that Cartesian space of every possible combination. I don't know, I just go home and come in the next day. Like, I just let it run. This actually goes back to my earlier point though, right? Where like the pipeline object, that's computationally expensive. But if you run it once over the weekend and you come back in and 72 hours later or something it's done, 48's a weekend, yeah, I'm a data scientist. At that point, you can publish this final fit object, and from then on, you're just pulling it down, right? And then you're just calling score, and it takes less than a second. And that's a big win of actually being able to use these. Any other questions? I have no time, so. Thanks, everyone. It was great.